Hello, we are starting the class. We almost finished the Debye model. I just don't want to repeat myself again, but the point where we finished yesterday, we looked on CV as a function of t. We can divide it by 3n, and what we've seen that the behavior at low temperatures was proportional to the temperature to the third power. I write down again the expression that we had.
Yes.
Ken,
Would you open the camera in the Google Meet, please?
what? Sorry, repeat.
Can you open the camera in the Google Meet? Yeah. It is slow.
As a second.
Good, thanks.
So we have CV divided by 3n, and the expression for CV, remind you, was as follows. So CV was 3 volume divided by 2 pi squared c to the third h bar to the third k Boltzmann to the fourth t to the third, an integral from 0 up to h bar omega dBi divided by k Boltzmann t, and here we have u to the fourth, e to the u, and e to the u minus 1 to the second power du. Okay? Now, omega dBi was omega dBi was 6 and c to the third pi to the second divided by the volume in 1/30. Okay, great. So what we've done first this low temperature behavior, and when t goes to 0, whatever we have here in the upper limit of the integral goes to infinity. H bar omega dBi divided by k Boltzmann t goes to infinity when t goes to 0. Now, we have an integral. This is how we obtain this t to the third. We have an integral, which is an integral from 0 to infinity of u to the fourth e to the u divided e to the u minus 1 squared du. Now, the claim is that it's converging to a number. We call it a. It's related to a zeta function. This is a Riemann zeta function. It doesn't really matter what this number is. Pi to the second divided by like 5 factorial. Doesn't matter. A constant number. The point is that this integral is converging. Although we have e to the u over here, and you might think, oh, it's exploding. For large u, in the denominator, you have e to the u to the second power. So e to the u and the second power, so when u is large, we have u to the fourth, e to the u, divided e to the 2u. Okay? So we have u to the fourth, e to the minus u, and this integral is converging. So since this constant is independent of the number of particles, independent of anything, basically, we have that CV is proportional. The only place where we have any dependence on temperature is here. So CV proportional to t to the third. And this is the expectation from any theory that's somehow related to experiment, right? And this is exactly the place where Einstein model failed. So hooray, we succeeded. This is one limit. The other limit is when t goes to infinity, right? You have to see either our theory is consistent with the claim that it's converging to a constant. And this constant is basically independent of almost anything. Okay, so what we have to do, we have to again solve this integral. The prefactor stays the same. So in the t to infinity limit, we don't care about this prefactor, right? Because, well, it's already constant multiplied by t to the third, so you don't care. The only thing that you care about is what happens to this integral, because in this integral there is some sort of dependence on t that sits in the upper limit of the integral. Okay, so let's see what happens. So when t goes to infinity, the only thing that in the integral that depends on the temperature is h omega d bar by k Boltzmann t, and it goes to 0. So when it goes to 0, we know, or all the way, that u inside the integral is somewhere between 0 and this h bar omega d divided by k Boltzmann t. Okay? So what we say that u inside this integral over here is small. So when u is small, we can expand all the exponents over here up to some, but you're using Taylor expansion. So first of all, so we have e to the u, which goes as, let's see what happens. All right. Hopefully you can see, because let's try to see if. Okay. So e to the u goes as 1 plus u, approximately. We're looking only on small u's. Okay, so we're doing this up to the first order. Now, even you don't need to do it at first order where you're looking on the denominator, because here 1 is enough. But in the denominator, where you have e to the u minus 1, well, you can say it is approximately u. Okay? Now, so let's substitute everything inside this integral. So what we have, an integral up to h bar omega d divided by k Boltzmann t of u to the fourth. Instead of e to the u, we write 1. And in the denominator, we have u to the second power du. So we have an integral from 0 up to h omega d divided by k Boltzmann t u to the second power du, which is 1/3 u to the third power. Right? It's not u. Let's write it down properly. It's 1/3 h bar omega d divided by k Boltzmann t to the third power.
But the exponent here is the power of 4, of u. Why did I say 4?
Yeah?
So it's supposed to be 1 plus u.
No, you don't need it. You see, the moment that you... So what will happen is that this additional u will contribute additional terms, which are going to be of higher power of u, that will contribute this number to another power. So it's going to be plus,
Yes.
plus something, okay? Which will
No,
look
of
like
course
1
it's
over
like
t to the fourth.
inconvenient.
No, it's not about convenience. It's not about convenience. It's about when I'm taking the limit when t is large, what should I leave? So I'm always leaving the non-zero leading order. So if the leading order is 0, I'm taking the next one. So the leading order is this guy. Okay? Everything else there is going to be a constant multiplied by 1 over t to the fourth power in temperatures, high enough temperatures, this is much larger than the next term, so I don't care. That's it. In all those expansions, you always take the leading order, the next order, and unless when the leading order is 0. Great. So let's plug in into this integral all the information that we have. Okay. So first of all, we know what the integral is, and CV is 3 volume 2 pi squared c to the third h bar to the third k Boltzmann to the fourth t to the third, and what is left is just the solution of the integral, which is 1/3 h bar omega d by k Boltzmann t to the third power. Okay, so first of all, a lot of stuff goes away, right? Like what? So 3 and 3 goes away. So we have V. Here we have k Boltzmann to the third. Here we have k Boltzmann to the fourth. So it's k Boltzmann. Okay, t to the third, they disappear. We have omega d by. On the downside, so 3 we cancelled out. We have 2 pi squared c to the third. Omega d by to the third. Right? Anything else that I forgot? Hopefully not. Okay, now, how convenient that we have omega d by to the third, and in the description of omega d by there is 1/3, exactly the same power, so those powers cancel out. So we have V k Boltzmann 2 pi squared c to the third, and instead of omega d by to the third, we have 6 n c to the third pi squared divided by volume. Pi squared, c to the third, volume, 2, 3. We obtain extremely nice formula that CV equals to 3n multiplied by k Boltzmann, or CV divided by 3n equals to k Boltzmann. So this universal constant with all the solids, if we know how approximately many particles there are inside the system, this constant over here is always k Boltzmann. This is what we got also with Einstein. Right? So that's interesting. If you take Einstein theory, that's definitely something wrong with that. It's too simple. You take Debye theory, which is much more complicated, but they still give you the same result. And what is even more wonderful is that it's also what you'll see in the experiment. Okay.
The question is, does it work with the lower half as well? Because this is the thing that we care about.
So what with lower what?
If it works with lower temperature.
Yeah. So Einstein and Debye works here together, but Einstein, it's basically wrong in this region. Why it's wrong? Because the convergence to 0 is much too fast. And now we understand that no, you need to use the Debye and this phonon description in order to properly understand also the low temperature behavior. Now, this is a great success for the theory. Right? So it coming 2 or 3 years after Einstein, it's a great success. What we now need to understand about the system. The Einstein formulation was very simple. Too simple. Right? The formulation was, we have a system of a lot of independent particles. Those particles, all of them are simply harmonic oscillators. They don't care about each other. So independence leads to factorization, and it was by hand inserted into the system. What Debye did the following, is that Well, the particles, whatever they're doing it together. Somehow, different particles together, vibrating, moving, up, down, right, left, but they're doing this together. And in the moment that you forget about this motion in cohort of many particles, you lose whatever happens at the low temperatures. So what we can understand that at low temperatures, somehow the system prefers a cooperative motion, okay, of many particles together. Those are those phonons, okay, that they're described as oscillations inside the system. But the physics of harmonic vibration, etc., it stays the same. It's just whatever you need to understand about the system, that everything is moving together somehow and not just independent particles. On the other side, for high temperatures, you don't care, because in the Einstein model, you don't care about any interactions. You don't care about cooperative motions. All of this is just out of the window, and probably also in the Debye system, because it gives you exactly the same constant, K Boltzmann. So for high enough temperatures, indeed all the particles, they're any particle doing completely independent motion, completely independent behavior when compared to everybody else.
Okay, but why they synchronize? Why suddenly?
What do you mean, why?
Why?
Why? So the physics of the low temperatures is such that they prefer to synchronize. Right? So what you introduced into the system? You introduced probabilities, right? You have Fi, which is 1 over z e to the power minus beta of some ei. You have competition between temperature and energy. And somehow, in low energies, the particles or the modes that exist in your system are just cooperative modes. So think about it as from perspective of a wave. Okay? So it's not small wave, some vibration over here and some vibration over there. What it describes that the whole system somehow moves together. Okay? That's what survive at low temperatures. Those are the modes that are surviving over there. This is the why. At low temperatures, the only modes or the only vibrations is when they trying to move together. The interactions, the energies are very, very important. High temperatures, the temperatures is high enough such that all the different vibrations don't care. So if you want to think about it, we'll explain it in a second. There is a potential energy and there is a kinetic energy. Okay? For any particle there is a potential energy and a kinetic energy. We eventually described everything by using quantum representation of the energies, but this quantum representation uses both kinetic and potential. But for each particle, we know there is a kinetic energy and potential energy. Now, for high enough temperatures, what we will see is that the kinetic energy is proportional to what? To the temperature. Okay? The kinetic energy of a single particle is eventually proportional to the temperature. We will see that 1/2 mvi squared average is K Boltzmann T. Okay? So the moment that your temperature is high enough, the kinetic energy of each single particle is just huge. Huge compared to what? Huge compared to the interaction energy with everybody else in the vicinity of the particle. So it's basically behaving as particle which is almost free, with some corrections due to interactions. Okay? Now, but the moment the temperature is low, your kinetic energy going down, and the potential energy becomes important. The interactions become important. They're always there. And when the interactions are important, particles start to somehow move together, and we know this motion together is oscillations, which leads to this part. So it's all in free energy, kinetic energy, potential energy, entropy. Somehow it always one part wins. In this part, the entropy and the kinetic energy is the important part, and the dependence or independence of the particles is irrelevant. In this case, it's very, very much relevant how the particle interact, okay? And the kinetic energy is less important. So this is, you have two different descriptions. In Einstein, no interactions in the first place, so you never can obtain this part because you have no interactions in the model in the first place. Okay, so here we finish the Debye model, but there is still a question that needs to be asked. Why K Boltzmann? So why this result that we have for many solids, we take CV divided by 3n, we obtain a K Boltzmann. Is this, and it happens in many solids. So we understand this is a cooperative vibrations of different phonons that live inside solids. So we understand this part. This part, what we're saying, well, Stas, you claim that there is a K Boltzmann T, okay? There is a K Boltzmann T in the system, and maybe everything comes from this K Boltzmann T, that everything inside your system is proportional to K Boltzmann T, and that's it. So the only energy that you have 1/2 mvi squared, right? And it's proportional to K Boltzmann T. So this is my energy. So the energy is going to be 3n. Okay, I have n particle. For each of them, I have motion in the x, motion in the y, motion in the z. Okay, so the average energy is going to be 3n, the average of 1/2 mvi squared. Okay, so it's going to be 3n K Boltzmann T. Okay. Take a derivative of this. So CV is dE to dt. Okay, and we obtain 3n K Boltzmann. So it works, right? So this claim that, oh, I only care about the free energy, it is fine, this is good, this is great, this is exactly predicts to me the K Boltzmann, the appearance of K Boltzmann over here. The only thing that is wrong is that the 1/2 mvi, it's K Boltzmann T, approximately K Boltzmann T. But if I want it to be exact, I have to put 1/2 over here. Okay. We'll show in a second why, where it's coming from. So if I'm looking on the kinetic energy, it's not just K Boltzmann T, it's actually 1/2 K Boltzmann T. So if you're talking about of specific numbers, exact numbers, okay, and you don't have K Boltzmann T, so you have 3n multiplied by 1/2 K Boltzmann T, so you should have 3/2 n K Boltzmann. And all the experiments show that it's not 3/2 n K Boltzmann, it's exactly 3n K Boltzmann. So we're close with this claim. It's somehow related to the kinetic energy, but the prefactors are wrong. Right? So it's not just the kinetic energy, something else is living inside the system. Okay? And we'll have to discover and explain this. So maybe there is a general claim why it's exactly K Boltzmann, and we understand that it's somehow related to the kinetic energy of the system. And maybe classical kinetic energy on the system. Okay? Any questions about the Debye model? Because what we're going to explore now is why this K Boltzmann, why it's so general, and that it's actually general and it's not related to solids at all. It's related to something very general which is called equipartition theorem. So before we're going into this equipartition theorem and classical partition functions, do you have any questions about the Debye model? No questions. Great. So what we are going to explore now is the classical partition function. Because if I'm talking about classical energies, I have to explain to you a little bit, although you have seen it in the class on thermodynamics, what is the classical partition function for the canonical ensemble. Okay. So what is that, or classical partition function? Now, when you treated this canonical ensemble classical partition function, you treated it as we have a phase space, we have to integrate over all possible momenta, and we have to integrate over all possible positions, all right? And I'm sorry, and you have to divide it by a specific point or a specific area or your phase space. Why exactly to divide it by the specific area of your phase space? Nobody really explained to you. Okay, it's not really clear from the classical perspective, but it's there. Okay, so this is the Gibbs, not factorial, but this claim. So if I have a single particle, I have three-dimensional space. So I have 1 over h to the third power, right? No, so it's 1 over h to the third power. And I have an integral from minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. This is x and y and z. Okay. And I have again minus infinity to infinity over px minus infinity to infinity over px, py, sorry, minus infinity to infinity over pz. And what I have here is e to the power minus my beta, the Hamiltonian, which is going to depend on x, y, z, px, py, and pz. Okay? And here I should have dpz, dpy, dpx, dz, dy, dx. Okay. So this is the classical partition function. It's very long and much more uglier than the point, than whatever we have for describing this class in the sums. But it's the same idea. You sum over all possible states. What are states now? Is you take your phase space, as Bina told you, and you divide it by small rectangles with the area of each h to the third. Okay? And that's it. So you count this guy, you divide it by h to the third, and you obtain the partition function. Exactly why and how, it's not for today. Yes?
How is it exactly different from the partition function we defined in class?
Why do you have this guy?
Oh, it's just to normalize the
Why h?
We really just need a measure.
Exactly. So you need a measure, and the question is, why do you need a measure when you're looking on a continuous space?
We want to define a measure of space, so we could count.
So you have to. So the explanation is you have to count somehow. If I'm integrating, what's the problem with integration?
Oh,
and why do? Let's give you a number.
And normalization.
What?
Units and normalization.
To what? What exactly those units? What are exactly those units? And why is the problem? The question is a little bit philosophical, so we'll live with it, but it's almost the same. The idea is the same, but when you look on states, you don't need anything of it. You just count states of the system. But for a continuous and classical system, it's hard to describe what is a state. There is nothing like a state for a classical system, right? When I'm looking on a behavior, for example, px, and this is x, and I have mathematical pendulum, okay? It will look like this, okay? So it's go from one point to another, okay? And when I'm saying, what is the state of the system? What is the state? So you think a point is a state, not some microscopical area inside the phase space. So this transition is a little bit sloppy. It is a little bit sloppy. Why? Because in the first place, okay, you don't really have states in classical perspective. It's not state. Nothing is a state of a system. So if you want to talk about states, this whole contour is a state. This specific point is not exactly a state. But let it be for a second. So, but this is our classical partition functions, which is a summation, which is an integration of e to the power minus b. This h you have to integrate over all your px's or your py's, etc., etc., etc.
You don't really need to discount dz, dy, dx because we assume in our model that all the energy is somewhat kinetic. No?
I haven't told you that. Wait a second. It's not about our model anymore. It's about a general perspective about of what a partition function, classical partition function is. Okay. What a classical partition function is. Now, let me look on a specific, okay, a specific way where how we treated this this guy. So first of all, what is the perspective of Hamiltonian? How the Hamiltonian looks like? The kinetic energy plus potential energy, right? Okay, now kinetic energy is always the same. Px squared divided by 2m plus py squared divided by 2m plus pz squared divided by 2m, right? Okay, now what about the potential energy? Now the potential energy, the thing is, the moment that the potential energy becomes complicated, usually you cannot do the math, right? So there are not a lot of integrals for the method that you know so far. There are not a lot of integrals that you can solve for general u of x, y, z. Okay, so we have to be a little bit more specific of what u, x, and y, and z is in order to be able to solve this damn partition function, right? The moment that there are some crazy u, x, and y, and z, well, you don't do it, basically. So the physical assumption, as usual, is to take something simple, but it's something that is still physical. And the assumption is, well, it's like the Einstein idea, right? Let's take what? Harmonic oscillators, right? So everything eventually is some sort of a harmonic oscillator. In the string theory, everything is it's always the same idea. Physicists are damn people. We can think about harmonic oscillator and that's it. And modification. So everything is harmonic oscillator. Yes. And actually you can prove it. Okay, so what you do, you look on this and you say, well, it is ax squared plus b, not beta, plus by squared plus c z squared. Okay? Why do you do this? Because you can solve it. And because everything is almost harmonic oscillator. So, but the idea is, let's look on the system. Where we have a kinetic energy. The kinetic energy is always quadratic in px, py, and pz. It's always quadratic. So there are absolutely no assumptions. But we also assume that the other part, okay, the potential energy, is also quadratic. Okay? This is your assumption. So the statement is you have such and such amount of degrees of freedom, and each degree of freedom is quadratic, have a quadratic contribution into your partition function. Okay? Now, so what happens if I have this guy? Let's write down all this long mess. So we have 1 over h to the third, h, not h bar, h to the third of an integral of e to the power minus beta, and here we have px squared divided by 2m plus py squared divided by 2m plus pz squared divided by 2m plus ax squared plus b y squared plus cz squared dpx dx. Yes?
No, I thought it would be easier to write half, like
Half. It doesn't matter. I will explain to you in a second why nothing matters over here.
It's you get
What?
Gaussian.
Exactly. I have a bunch of Gaussian integrals. Now, let's look on the integral of this form. It's always from minus infinity to infinity, okay? So, what I have here? So I have minus infinity to infinity 1 over h to 1/2 e to the power, 1/2, minus p, or beta, minus beta, px squared divided by 2m, dpx. Okay, so this is one integral. I also have 1 over h to 1/2, an integral from minus infinity to infinity, e to the power minus beta, py squared divided by 2m, dpy. I have also an integral, they're all independent, right? Minus infinity to infinity, 1h to 1/2, e to the power minus beta, pz squared divided by 2m, dpz, an integral 1 over h to 1/2, minus infinity to infinity, e to the power minus beta, a x squared dx, an integral from minus infinity to infinity, 1 over h to 1/2, e minus beta, b y squared dy, an integral minus infinity to infinity, 1 over h squared e to the minus beta c z squared dz. Okay, so I have a multiplication, I have sixfold integral. The moment that I wrote down this form as a quadratic form, this nasty integral is just a multiplication of 6 very nice integrals. Why they are nice integrals? Because they're Gaussian. And you've seen at least twice what is a Gaussian integral, right? So I by myself proved to whoever took this statistics class, right, how exactly to solve this integral. I won't solve it again to you, but I'll just use the formula. Now, if you really want, I can prove it to you, but it will take me 5 minutes. So let's look on an integral of e minus infinity to infinity e to the power minus what we have here, z squared, and let's put it lambda dz. Okay, so this is the Gaussian integral. What's the solution of this Gaussian integral?
It's a pi over
Square root of pi
lambda.
over lambda. Okay.
Yeah?
Yeah. Maybe you're wrong, but it's fine. You can always check yourself, right? Because you know that the integral from minus infinity to infinity e to the minus x squared divided by 2, 1 over square root of 2 pi dx have to be equals to what?
1.
1. You can check if this works. Why it's equal to 1?
Because this is a normal distribution.
Exactly. So it is the density of the normal distribution, and the integral over the density from minus infinity to infinity have to give you 1. The probability that something will happen have to be 1. Okay? The second most important phrase from the probability class. Okay, so we are using this formula for all the 6 integrals. 1, 2, 3, 4, 5, 6, 7. Oh, 6. And so what we have? Each of the integrals. So let's solve the first one, and then it will be clear what happens to everybody else. So we have 1 over h to the half, an integral from minus infinity to infinity, e minus beta px squared divided by 2m dpx. Okay? If you're taking an integral over px or py or pz, x, y, z, doesn't matter. It's your integration integration variable. So according to this formula over here, we have 1 over h to the half. This integral contributes a square root of pi multiplied by 2m divided by beta. Okay? Okay, so we're using now this formula for whatever integrals what we have over here. Okay, so z equals to 1h to the half square root of pi 2m beta multiplied by 1 over h to the half a square root of pi 2m over beta, 1 over h to the half square root of pi 2m over beta. What else? 1 over h to the half a square root of pi over a beta, 1 over h to the half a square root of pi of d beta, 1 over h to the 1/2 square root of pi to the c beta. Okay. Now, what we do next, remember that the universal behavior for high temperatures was obtained for what? For the energy, right? So we have to compute somehow the energy. Okay. Now, in order to compute the energy, we don't need Z. What we need? Ln Z. So the logarithm or the partition function is, well, you have a lot of stuff inside, right? You have a lot of stuff inside, but the only thing that we care, because Cu or E, it's d to the beta with a minus sign of log Z, and afterwards Cv is going to be dE to dt. Okay, so yeah. So the only thing that you care about is t and beta, and everything else should be absolutely unimportant, right? So we have beta, and everything else, well, you don't care, right? You don't care. So ln Z, it's a bunch of constants, huge bunch of constants. If you want me to write it down, I will write it down. It's 1 over h to the 3/2 of a square root of 2 pi m to the power 3 log. And also I have 1 over h to the power 3/2 of a square root of what? 1 over a, b, c, and multiplied by 1 over beta to the third. So we have where? Here?
Yes.
So pi to the third. Okay. Do I care about this? I don't care, because it's a log of 1 over h to the power 3 without a bar, h to the power 3 of square root of 2 pi m to the third, square root of pi to the third a, b, c, okay, minus 3 log of beta. Right?
Yeah, but it's really don't matter.
Yeah, so all this constant,
Yes.
it vanishes. When you take E equals to minus d to d beta of log of z, right? It's minus d to d beta of minus 3 log of beta, which gives you 3 1 over beta. Right? So it is what? 3 multiplied by k Boltzmann T. Okay, and now the last part. Cv equals to dE to dt equals to 3k Boltzmann. So you take one single particle, and this single particle have kinetic energy, and for their potential energy, you have quadratic representation. And the classical theory tells you, well, it doesn't matter what are your M is, it doesn't matter what's the strand, what A and B and C. It doesn't matter if you divided or haven't divided by any H over here and what exactly this H that you've taken over there, right? All of this is completely irrelevant because the moment you start to divide and take derivatives, all those constants, you don't care about them, okay? And the specific heat is just 3 called K Boltzmann T. Okay. Now, so we had, think about where it came from. It came from the presence of beta for each degree of motion, for the kinetic energy and the potential energy. So you see beta came from here, 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 and beta came from here. Now let's take the contribution, not of everybody together that gave us this 3 number, but let's look on the contribution of each single degree of motion, kinetic or potential energy. Okay. So we have, for example, Z1, okay, and it's a multiplication. Z1, it is, well, whatever. Let's call it 1 over h to the 1/2, a square root of 2 pi m divided by beta. Okay. Now, log of Z1 is going to give you what? A log of 1 over h to the 1/2, a square root of 2 pi m, multiplied by beta to the power minus 1/2, which is a log of 1 over h to the 1/2, a square root of 2 pi m, minus 1/2, right? Minus 1/2, minus 1/2 log of beta. Okay. The next step is, all right, so E1, the contribution, the average energy just to this one specific degree of motion is what? E1, it is what? Minus d to the beta, minus d to the beta of log of Z1, which is, you don't care about this part, it's independent of beta, you only care about that part. And what it gives you, it is minus or plus 1/2 1 over beta. It is 1/2 K Boltzmann T. Remember that 1/2? That's where the half came from. Where the half came from? From the Gaussian representation, or for the quadratic part of the energy. Okay? So if you have quadratic parts of the energies, each of those quadratic parts, according to what we've seen here, will contribute your 1/2 K Boltzmann T. Okay? So this is going to be E1 will give you K Boltzmann T, and CB1 is dE1 to dt. It will contribute 1/2 K Boltzmann. So this will give you 1/2 K Boltzmann. This will give you 1/2 K Boltzmann. This will give you 1/2 K Boltzmann, etc. for this and that and that. So the average energy, it's always 1/2 K Boltzmann T, as long as this energy is represented by some quadratic form. It doesn't matter if it's a kinetic energy, it doesn't matter if it's a potential energy. So anything that you have and it behaves as quadratic something, okay, produce this 1/2 K Boltzmann. So we have in total 6, okay, so CV equals to CV1 plus CV2 plus CV3 plus CV4 plus CV5 plus CV6, which is 6 multiplied by 1/2 K Boltzmann, which is exactly 3 K Boltzmann. So the general statement that I proved over here, it's called the equipartition theorem.
Yeah, but like you assume.
I'm not assuming anything. I'm saying if the classical representation is correct for the partition function, each degree of freedom equipartition theorem. Each degree of freedom that is represented by quadratic form of the energy gives 1/2 K Boltzmann for the specific heat. Capacity. So even it's more than that, it's also the average energy, right? We know that the moment that our energy is just quadratic, the average energy is 1/2 K Boltzmann T. This is why it's always some sort of a scale in thermodynamics, in physical chemistry. If you heard something about, you always talk about, oh, it's K Boltzmann T, K Boltzmann T. Why K Boltzmann T? This is your scale. This is approximate, not approximately, this is your kinetic energy. How fast this thing is juggling around, on average, is 1/2 K Boltzmann T. Okay. This is why the Einstein model, the Debye model, and any model that will describe solids, which for high enough temperatures, that just particles that are somehow rotating and don't care about each other, all those models will have to give exactly this result, that the specific heat capacity, it converges to a constant, and this constant is K Boltzmann multiplied by the number of the degrees of freedom that you have. Okay? And when I'm talking about the degree of freedom, I'm making a separation between the degree of freedom that gives rise to kinetic energy and the degree of freedom that gives rise to potential energy, because I'm looking on the degrees of freedom in my phase space, right? It's not just x, y, and z, because in my phase space it's x, y, z, px, py, pz. Those are different degrees of freedom. Okay. Very nice. Very, very nice. This is why we understand completely the Debye model. It's not only the Debye model, a lot of other questions as well. But if you're already treating this classical partition function, are there problems with the partition function? Right? So if I'll take the partition function of an ideal gas, right? So this is Gibbs paradox. What is a Gibbs paradox? Oh great, we devised a machine, this partition function, that describes to us everything. The moment that you calculate the partition function, you know exactly, by taking the appropriate derivatives, what is the pressure, what is the average energy, what the average magnetization, whatever you want to know about your system, you take from some derivative with respect to some conjugated variable, voila. There are many different variables, many different derivatives that you can take, but the original quantity that you have to compute is the partition function. Okay? So the simplest problem to try and solve is ideal gas in a box. Right? So we take particles. The particles are sitting inside this box somehow, right? They're sitting inside this box. V, volume of the box. And all the particles, it's ideal gas. Meaning they are not interacting. The only interactions is with the wall of the box, and they cannot escape the box. Right? They do not hit each other, there are absolutely no interactions. The simplest possible thing that you can imagine. Okay, so let's see if this partition function that we just written a couple of minutes ago and you've developed it in the class on thermodynamics would work or have to work for this case, right? So what is z? So we have integration from minus infinity to infinity over px, minus infinity to infinity over py, minus infinity to infinity over pz. We have 1 over h to the third, okay? And we have an integration of x, y, z such that an integration over volume of the system. Volume of the system. And here we have e minus beta, px squared divided by 2m, p plus py squared divided by 2m, plus pz squared divided by 2m. We absolutely have no interactions between the particles, so we have only kinetic energy, and the interaction with the walls is described as what? As boundary conditions. The particles cannot escape the volume, this box. So we have dpx, dx, dy, dz, dpx, dpy, dpz. So what I've described over here, I've taken one particle, this one, and I have written the partition function of this specific particle. Okay. Now, why I'm troubling myself in writing the partition function of one specific particle? Because if they're independent, and the total energy is just the sum of the energies of all the different particles, right? So I'm going to use the factorization. I will compute the partition function of one of the guys, okay? And then multiply it. Because all these z1, z2, z3, z4, z5 are going to be exactly the same, right? All the particles are identical. Okay, so what happens in this integral over here? Let's see. So integration dx dy dz is its integration over the volume. So we have the volume of the system divided by h to the third, an integration from minus infinity to infinity of e to the power minus beta px squared divided by 2m dpx, an integral from minus infinity to infinity e to the power minus beta py squared divided by 2m dpy, and we have an integral from minus infinity to infinity e to the power minus beta pz squared divided by 2m dpz. Okay? Great. Why? Because we know that all of those are just Gaussian integrals, and they exactly the same, right? And we use the formula that we have written a couple of minutes ago on the board. So you have v divided by h to the third, and the integral of this guy is what? The square root of 2 pi m divided by beta, a square root of 2 pi m divided by beta, a square root of 2 pi m divided by beta. Great. Yes? No interactions. So they are confined to the box. So this is why you here integrate just over the point. That's it. Okay, so you have z. Right, z1. Now you do the following thing. What is z? According to what we've learned before, it is just z1 to the power n. Right? Okay, so it's z1 to the power n. We know this. So it is simply v to the n power, h to the third 3n, and here we have 2 pi m divided by beta by n to the half. This is our partition function. Okay, great. So if you want to compute anything, well, let's write down the free energy and we're done.
3, no? 3n.
3n. So,
No,
where 3n?
2 pi n
2 pi
divided
n
by beta
divided by
is-
beta. So it's
is-
supposed to be 3n.
3n.
Yes.
Okay, thanks. Thanks. So what we have, f is minus 1 over beta log of z. Okay, we've seen it many times already. Okay, so it's minus 1 over beta log of what? Log of v to the power n h to the 3n. Okay? And here we have 2 pi n divided by beta to the 3 n to the half. Okay? And we'd like to write it down as f equals minus n divided by beta log over v divided by h to the third power and 2 pi m divided by beta to the power 3 halves. So we write it down, or Gibbs writes it down, and then he starts to scream, this is wrong. What is wrong here? Why, when Gibbs looks on this formula, he says, very bad formula, very bad Gibbs, very bad partition function.
The energy supposedly decreases with respect to
It's free energy, it's fine, it's still
And-
fine.
No,
What,
but-
was our first assumption? First assumption in the first lecture. First assumption. I started this semester with single assumption. What was it?
Extensivity.
Extensivity. Right? So if I increase my system by the size of 2, will the free energy grow by a factor of 2? I have to put 2n particles and I have to put the volume to increase it also by 2. If I increase my volume by 2, okay, will this also contribute to the extensivity of f? No. The moment that I have this logarithm that sits inside, or this volume that sits inside the logarithm, and it's not divided by n, not divided by anything, okay? This means that f is not extensive. F is not extensive. F is not extensive. It's a huge problem. Our first, I will take your comment a second. The first assumption was everything had to be extensive. We work out very hard. Bina works out very hard. We describe to you these partition functions. We try to solve the simplest problem, and it goes wrong. Okay? Yes.
Won't we have to also increase h to the third power? by-
No. No. What is h? As you told me, it's just normalization constant, right? You told me that.
Yes, but it is specific to the system.
No. So what? It's a constant. It cannot be specific to a system. Moreover, you're claiming it has to be specific to the number of particles and the volume and etc. Nah. What Professor Gibbs, I think he was a professor, done in order to solve it? Whatever any good physicist will do, right? So what's the problem? If you look on the, and it's always worked like that. Just don't try to do it in an exam.
But why is it extensive?
Increase everything by 2. The number of particles is increased by 2, increase the volume by 2. Does F...
You need to divide the volume by n. No?
Oh, really good. So when I look on my formula, and I look on my formula, this is my formula. F is minus n divided by beta log of v, okay, divided by h to the third, and I have 2 pi m divided by beta to whatever, 3 to the half, okay? It's not extensive. This factor is fine. When I increase n by 2, I have a factor of 2 over here. But the moment that I increase n by 2, I also have to increase the volume by 2. And here I have, well, additional 2, a log of 2. Log of 2 is not 2. Sometimes it is, but for us it's not. Okay? So if I increase the volume by 2, the system is not increasing by a factor of 2. So somehow I have to cancel this. And what you're proposing is exactly what Gibbs suggested. We need to modify something such that V will be divided by n. Okay? This is somehow what that we need to introduce into the system, that this n will appear here. So what can we do in order to do this? So Gibbs looked on it and he had a wonderful idea. He knew that this should be the right solution. It's always like that. But when you have a hard problem and you have a physical intuition, you try to tailor your solution such that it will fit your intuition. And because the space of all possible solutions and all possible ways to attack a problem is infinite. So you have to choose. And Gibbs knew how to choose because he knew that this n should appear over there. So what Gibbs done, he said, I know how to plug this n inside. It's not that I have to plug it at this stage. This is bad, right? So you have a final formula and you say, oh, I have to divide V by n. You have to modify something more conceptual. And the thing is where this n can come from. So Gibbs looked on this, said, well, if I have this, so let's look on this original expression. Z was Z1 to the power of n. Gibbs said, well, let's play with this expression. Okay, this expression. Let's introduce something like 1n factorial. What it gives us? The introduction of this 1n factorial. So let's do again all the mass that we have inside by introducing this n factorial. So if this is this, so we have f equals minus 1 over beta log of what? Log of z, which is minus 1 over beta log of whatever we have, which is this part, v to the power n 2 pi m divided by beta 3n to the 2 divided by h to the 3n, and we have 1 over n factorial. Okay, so we'll split it. We have minus 1 over beta log of v to the power n h to the 3n 2 pi m divided by beta 3n to the half minus log of n factorial. Okay, now, if n is not 2 or 3, if it's actually 4, we can, or even 3, we can use the Stirling approximation for n factorial, right? So what is the Stirling approximation? Stirling. So what Stirling tells us, it's minus 1 over beta log of v to the power n h to the power 3n 2 pi m divided by beta to the 3n divided by 2. And here we have minus n log n plus n. Okay, so if we do this, so what we obtain mathematically, only mathematically. Remember, the goal is that somehow v will be divided by n. So first of all, we take all the n's from here out. This n, this n, and this n, we take it out. Okay. And we obtain that the free energy minus 1 over beta. We have n log, what we have inside is v h to the 3 2 pi m divided by beta to 3 halves minus n log n plus n. Let's take n out, so we have minus n divided by beta. And here we have log v, and we introduce this logarithm into this logarithm. So we have v divided by n, 1 over h to the third, 2 pi m beta 3/2 plus 1. So, well, the goal was achieved, right? So we have v divided by n. So any increase of the volume by factor lambda will be cancelled out by increase of the number of particles of the same factor lambda. So this will cancel out. It does not affect the one. So if we increase the size of the system by a factor lambda, the free energy will also be increased by a factor lambda, right? So if n goes to lambda n, v goes to lambda v, we observe that f goes to lambda f. This is extensivity. Okay? So mathematically, and only mathematically, Gibbs understands that you have to introduce this prefactor 1 over n factorial. The question is why? Okay. The question is, so you solve a problem, you solve the math is correct, everything fits, right? The question is, why have you done it? So the idea was of Gibbs, oh, and this is right. We've talked about ideal gas. The particles are identical. So what do I mean by identical particles? So let's assume that we have particle red and the particle blue. Okay? So those two particles, the positions of those two particles, it's a state of the system. Okay? Now, if I switch them, okay, and I'll plot a blue particle and a red particle, so this was my box, my original. This was my original box. And I switched red and blue particles. Right, so and I switched red and blue particles. So now I have red and I have blue. You can tell me, Stas, it's a different state of the system because this is blue and this is red, and this is red and this is blue, so it's a different state of the system. But if you had two red particles, so the particles are not identical. So if you have two red particles, one over here, another one over there, and they have somehow switched, right? So this is not two different states of the system, it's exactly the same state. Okay? So the idea is, oh, I have to divide by some n factorial because I count on the total number of states inside my system. Remember, z comes from summation of the total number of states. So I overcounted. How I overcounted? All the different switching of all the different particles between themselves, okay? It's overcounting. Because all the particles are identical to each other. So when you switch them, you counted this as different states, right here, but no, it was forbidden. This is exactly the same state. This is why I have to divide by n factorial. It sounds reasonable, right? But it does not work in classical physics. It does not work in classical physics. So even all the particles are exactly identical, okay? I can say the following thing. I still can identify different particles. Although they are different particles, although they are identical, I can call this guy Sasha and this guy Masha, okay? And I can follow them, okay? I start with a specific position when Sasha on the right, Masha on the left. They are doing something, and now Sasha on the left and Masha on the right, okay? this is the different state because I followed them. I know this was one configuration and I somehow followed them, and this is another configuration. Now, if I cannot count this state, I can follow the different particles. If I not allowed by Gibbs to count the state, so I don't understand something. Right? I started for a specific state, the system evolved, and it reached a different state, right? But Gibbs says, no, it's the same state. But I know this is Sasha and this is Masha. No, they're identical. You cannot call them Sasha and Masha. Says, well, okay, so whatever names do you want, not Sasha and Masha, Igor and Shmigo, it doesn't matter, okay? It absolutely doesn't matter how I call them. I can know this is particle 1, this is particle 2. Gibbs says, no, you cannot. Because if you can call them and you can identify them, this is particle number 1, this is particle number 2, then you can discriminate between different states. Because you start from one and you reach the other one. So those are different states. And Gibbs says, no, you can't. So the paradox, and this is truly paradox, you have to divide by n factorial. You don't know why, but it works mathematically, so you have to. Okay? Otherwise, your formalism is simply wrong. You have to divide by n factorial. You describe or you justify this division by n factorization by saying, oh, I have identical particles, and those identical particles, if I switch them, it's the same state. But at the same moment, you can say, but in classical physics, I know who they are, so I cannot switch them, and I can always discriminate between the states. And this gives us, you cannot. The paradox is, you're looking on a classical system, you're looking on identical particles, you can always identify them, you can always say at each point of time who is who, because you can follow the trajectories, and you're still not allowed to do that. So this word not allowed, this is a paradox, because if you can do that, you cannot justify the division by n factorial. So the paradox is you have to divide it, but the paradox still there. You're in classical system. You experimentally can follow each single particle inside your box, but you're not allowed to do that. Okay? And the realization of Gibbs' paradox, actually, so it was a paradox. It works. Think about it. You have a theory. Theory works great. No matter what you try to compute, almost no matter what you try to compute, it gives you fantastic results, like for the heat capacity. Okay? But inside this theory, there is a hidden problem. You have to do something that you do not really understand why you're doing so. That you're not allowed to do it according to the nature of the system. And you're familiar with a system where you're not allowed to follow single particles. In what system or in what reality we're not allowed, or we simply cannot follow single particles? Quantum mechanics. In quantum mechanics, the thing is, the moment that I know I can call them Masha and Sasha or whatever, right? And if I know explicitly what their positions are and who they are, I don't know anything about the positions in the next epsilon time. I absolutely have no idea where they moved. So in quantum mechanics, there is no trajectories, right? I cannot simply follow a single trajectory. You don't know the multiplication of delta x by delta p, right? It has to be greater than something. So in quantum mechanics, it is indeed not allowed. It's not just not allowed, it's the law of physics. You really don't know who is who. You can call them at some specific moment of time who is Sasha and who is Masha, but in the next moment of time, you don't know who is here. Right? So Gibbs' paradox is something that comes even in the classical description. It's something that comes from the quantum statistics of single particles. Okay? Why and how? And you already know that in quantum statistics, there are two different types of particles. There are fermions, there are bosons. Each of who you have to count differently. So, and how it's related to the n factorial and resolution of the Gibbs paradox, we will see next week. Thank you all. Happy Hanukkah.
תודה, לעצמך, חג שמח.
חג שמח.